Suppose we think a volcanic eruption is happening.
Exactly.
We can go there and we can monitor the volcano every minute and look at the internal dynamics, right?
This is out of Lawrence Berkeley National Lab and was published in the Physical Review, Accelerators and Beams.
The basic idea is, in order to make muons, usually you need like extremely large particle accelerators, okay? And these guys have done it in effectively the size of like a lab. And that becomes really, really relevant if you're trying to use muons to do CAT scans on very large things. For example, the pyramids or a volcano. It is one of the fundamental particles that is kind of like a heavy cousin to the electron, okay?
Heavy cousin.
A heavy cousin. And they were first observed in these things called cosmic ray showers, which are these showers that come when a cosmic ray hits the Earth's atmosphere. The flux is really weak. It's about 1 a minute through your fingernail.
Okay.
Okay. The muon is kind of like an X-ray in that the path that it takes, how far it gets through something, is dependent on the density of the stuff that it's going through. It can go through a lot more stuff before it gets stopped. Okay. So now you can start imaging things like buildings or volcanoes. They actually used it to map out the Great Pyramid of Giza. And they actually did find a void there. They found a previously unknown void. Again, though, there's a limitation.
Okay.
Because we are relying on cosmic rays, which the flux is so low, you're only going to get a static image. You need a year to take this photograph. You need a year to take this CAT scan. It would be really nice if we had so much flux, right, that I could get like a moving picture of what is happening in
that's the foundation of where the story now picks up from.
This paper came out in the Physical Review. It's going to be 40 times the particle delivery rate of cosmic rays, right? And it's an order of magnitude reduction in exposure time. Now you can start doing the same kind of muon tomography of your pyramid or whatever, but instead of taking like years, it's going to take maybe a few days. Right.
Which is like, for anyone who's trying to do any of these aspects of archaeology, geology, that time efficiency is, I mean, incredibly meaningful.
It's only the beginning, right? Because like these lasers now, they're going to get much, much better. Right now, these guys are doing like the top this thing can shoot the electron beam at is about 1 hertz, right? But we could be getting to kilohertz, which is thousands of shots a second, right? And then that's another 3 orders of magnitude above what we already have. And so now you can start doing, okay, instead of a few days, now you got a few minutes. We can, and then now that becomes really crucial.